The mathematical foundation of statistical mechanics is the law of large numbers. Let's consider a volume in which we place n particles. Every particle is free to move about this volume at a given speed, which is also freely available. Now also consider that n is very large. Let's say 10 to the 23, which is the number of particles maybe in this room. Then, if we would like to get a microscopic description of this system, we would like to know for every time point where every particle is in 3D space and also its velocity. Hence, in such a microscopic description, we would have 6n variables to fully describe the total system. Such detailed description would be completely useless. Now, our own perception is on a macroscopic scale. So in a macroscopic description, there's only a limited number, small number, of macroscopic quantities which we call observables. Typical observables could be the volume of the system, the energy of the system, maybe the mechanization of the system, pressure of the system, and the temperature of the system. Statistical mechanics deals with those observables. Now, observables concerned with aggregated quantities, which are typical averages of quantities that an individual particle has. As an example, let's consider the total energy of the system. Now, the total energy of the system is just the sum of the energy of every particle epsilon I. In our example, these particles would just fly around, and the energy is solely given by the kinetic energy of the particle. Now, there are particles which just are standing still. There are particles which fly at the speed of sound. That means the distribution of the energies of all the particles is a very broad distribution, characterized by a mean of the mean of epsilon I and a width given by sigma epsilon. Now what we could ask is, what is the mean total energy of the system? Well, the mean total energy of the system is again nothing else like the sum on all the mean and average energies of every particle. But what is now the width of this mean energy distribution, which we will call sigma E? Now, the width of the distribution is given by its variance. Variance is defined as sigma E squared is equal to the mean of the deviation of the energy from its mean squared, which just by multiplying out to the squared, we obtain this is equal to the mean E squared minus 2 mean E times mean E plus mean E squared, which gives the mean in E squared minus the mean in E squared. Now let's calculate this quantity, the sigma E squared, just by using this last equation and by letting E, which is appearing here, just writing this as a sum on all I epsilon I. Interchanging, taking means and taking sums, and assuming that the epsilon i's, all the epsilon i's are uncorrelated with each other, we derive to a very simple relation of the sigma in E and the sigma in epsilons. Namely that sigma E squared is equal to n times sigma of epsilon squared. Now we are ready to define the law of large numbers, considering the relative width of the distributions, meaning so we compare the width in E to the mean of E, and we see that this is given by the relative width in the epsilons, which is sigma epsilon divided by the mean of the epsilon i's, divided by the square root of the number of particles. Now let n now go to infinity. We see that the width in this aggregated parameter in the energy is going to 0. The result can be more easily described in a graphical way. Whereas the observable for every particle, in this case the energy, is described by a broad distribution, the aggregated observable, in our case the total energy, is a highly peaked distribution